Alright, we're going to do a quick tutorial on how to use OpenCV in ROS. This will be useful for your homework 8 and probably beyond. So last video we talked about how to represent images, and we found the image on the left, which is a black and white image, very low resolution of Abraham Lincoln, was really just a bunch of numbers arranged in a two-dimensional matrix, where a small number is a black pixel because not much light was emitted there, and a large number is a white pixel because it captured an awful lot of light in that spot. And then we talked about how color images are that two-dimensional matrix plus a little bit more, an extra dimension that has the red, green, and blue colors components of the full image so that you can represent the entire image in one handy three-dimensional matrix. So images are basically matrices. We know how to process matrices. You've probably done that in quite a few classes at this point. And it turns out that there are a number of libraries out there that can help us do this. So today we're going to talk about one of those libraries, OpenCV. OpenCV has been around since the late 90s. It was created by the Intel Corporation back when they were creating processors that were really good at certain types of math, especially types of math used for matrix manipulation and image processing. But nobody was really using it at the time because there weren't any handy libraries out there for it. So they took the initiative, wrote their own library for it, and it's since lived on in the open source community since. OpenCV is primarily written in C and C++, so it has great compatibility with that, but it also has wonderful Python bindings that we'll be using in this lecture and probably in the course going forward. And then of course there are a number of other bindings for OpenCV to MATLAB, Java, and pretty much any other language out there, so if you want to use it in other projects, you can look up the tutorials on that. OpenCV works really well with ROS. It contains a lot of nice image processing functions in it that we can use to make our robot understand what the world around it looks like, and we can make that work with ROS pretty easily. But we talked a lot about how to represent images. It turns out OpenCV image is not quite the same thing as the typical ROS sensor messages that's used. In ROS, when we're trading images between nodes, we typically use the sensor's message slash image type, and in OpenCV it's just a little bit different than that. But fortunately, this was such a common problem that people have written an easy conversion class for it. You instantiate the CV bridge class, you use the image message to CV function to convert from a sensor's message image to OpenCV. You use CV to image message to go back, and you're good to go. So let's say you want to make your own ROS package with OpenCV. Well, you end up using cat can create package, just like we've done for every package so far. This line should look pretty familiar to you. You have cat can create package, you have your package name, and then we have some dependencies you haven't seen before. We need to import the sensor messages component because that one has the image message that we've used before, and we need to import the CV bridge component so that we can use the CV bridge class to do our conversion. The rest of this line is just ROSPy and whatever other dependencies you have so that you can write your nodes that you need to write. So what does this node look like then? You create your package, you go to make a node. What does it look like? Well, we start pretty normal. We start with our normal user bin and Python on top so we can run it in Python. We import ROSPy, but then we have to import CV2. Now, OpenCV is its own library that's standalone separate from ROS. The good news is that if you have ROS installed, you most likely have OpenCV installed as well, especially if you have a desktop version installed. So we need to import CV2 as a separate library from ROS. It doesn't exist as ROS package, it doesn't exist in the ROS domain at all, so we import it as CV2 here. And then we import a ROS package, sensor messages, so you can import the image message that we're going to use to translate between different nodes so we can send our message out. And then you want to import the CV bridge that we talked about before so we can do our conversions. So let's say we want to make an image flipper. All this class is going to do is take in an image and flip it horizontally so that it is upside down, basically. Well, we have our normal stuff in the init function. We define a subscriber so that the incoming image on topic image can be received and run in this function flipper callback, which I'll be talking about in just a second, and a publisher for the flipped image, which is also using an image type to send. But we want to do one more thing. We want to instantiate our bridge class here so that we can use it through the rest of the class, so that way it only gets created once. We don't have to use it, create a new one every time we use it. So let's get to our function. Let's get to our flipper callback. What does this look like? Well, it's going to look pretty similar to most of the other callbacks you've used. You're going to take your message in, you're going to do some math on it, you're going to call some maybe OpenCV functions in this case, and then you're going to push the result back out onto another topic. So the first thing we want to do is take the incoming message, MSG, and convert it to an OpenCV image. So we use that bridge function I was talking about, image message to CV2. We give it the BGR8 type in quotes at the end there. This just tells it what type of OpenCV image we're expecting. BGR means it's blue, green, red order of color because that's what OpenCV tends to use, and 8 is for 8-bit color. Now you may want to use something different depending on your application, but that's what we're going to use for this class. Next, we do our actual work here. We call the CV2 flip function, which flips our image horizontally. The 0 here tells it which axis to flip over. The input image is a CV image, and then it goes into a new image, CV flipped. I call it CV flipped to indicate it's an OpenCV image and not a ROS image. You can, of course, use whatever naming conventions you like. But this is all we need to do to actually flip it. So now we're ready to send it back out. So we do our reverse conversion here. We use our self.bridge.cv2 to image message, put in the CV flipped message, tell it again it's BGR8 format, and store it in a new variable. And then we just publish this like normal. And the rest of this node looks pretty normal. We initialize our node in the main function, we instantiate our class, and then we spin forever waiting so that the callback can do its job. So a couple of notes here. If you've ever used NumPy before, an OpenCV image is really just a 2D or 3D NumPy array. So this probably makes your life a little bit easier, and if you've used arrays in other sorts of languages, then it's going to look very, very similar to you. So if we want to access a pixel value, we really just use array indexing. So here we have, if we want to know the value of the ith row, jth column, and kth color in an image, then we say image square brackets I, j, k, and that'll give us a number, in this case between 0 and 255 because it's an 8-bit image. Note here that K is the color channel, and this goes in blue, green, red order because of OpenCV. So 0 in the K column will give you the blue component of the image, 1 will give you the green component, and 2 will give you the red component. And we're going to talk a lot more about this when we talk about color in images and how to filter for color, because there are a couple of different formats you can use that aren't just blue, green, or red. Some of them maybe make a little bit more sense for color filtering than looking at just one component of the image like that. Last but not least, if you want to create a new image that's a subset of the previous image, so if you want to crop an image basically, then you use array slices in Python. And this is a really handy feature that lets us quickly and easily create a cropped image so you can just look at a subset of it. And this is what you're going to be doing in homework 8, so you should pay attention to this line here. We basically say image and then square brackets, give it the start position and the end position for the rows, the vertical portion, and then a start position and an end position for the columns, the horizontal portion. And that'll give us a complete square image that's a subset of the bigger image.